Hello, my name is Dustin Trujillo, and my presentation is titled Internet Key Exchange version 2, which is also known as IKE or IKEv2. Today's agenda includes the following items: taking a look at what Internet Key Exchange is, the context of IPsec, key management protocol of IKEv2, as well as key determination, supporting groups, and potential weaknesses of IKEv2. We'll also look at initial exchanges, and continuing on from the previous slide, we'll also look at subsequent exchanges, header payload formats. We'll dig more in depth into the payload types, as well as look at the notify messages. Before we dig into this slide, let's get on the same page. First, as a reminder, for previous lectures and readings in the CS 5920 class, our textbook refers to a security association as the establishment of shared security attributes between two network entities to support secure communication. What's more, in previous lectures and chapter 20 in our textbook, IPsec stands for Internet Protocol Security, and in short, IPsec provides capabilities to secure communications across a LAN, private and public WANs, and across the Internet. Now, building off these two fundamental concepts, let's ask, what is the Internet Key Exchange version 2? Well, in computing, IKEv2 is the protocol used to set up a security association, also known as SA, in the IPsec protocol suite. What's more, IKEv2 builds upon the Oakley protocol and Internet Security Association and Key Management Protocol, which is also known as ISAC-MP, and of course we'll discuss these two protocols more in the next slide. Getting back to this slide, IKEv2 uses X509 certificates for authentication and a Diffie-Hellman key exchange to set up shared session secret. What's more, it is from this shared session secret from which cryptographic keys are derived. Additionally, it is important to note that with regards to the X509 authentication certificates, both pre-shared and distributed certificates using DNS or DNSSEC can be used. In this slide, we will discuss IKEv2 in the context of the IPsec key management. As we recall from previous lessons in the class, the key management portion of IPsec involves the determination and distribution of secret keys. In other words, a typical requirement is 4 keys for communication between two applications. That is, transmit and receive pairs for both integrity and confidentiality. Additionally, IPsec architecture actually requires support for 2 types of key management, both manual and automated. So with regards to manual, this is where a system administrator actually manually configures each system with its own keys and with the keys of other communicating systems. Of course, this is only practical for small and relative static environments that don't change. With regards to automated, this refers to an automated system that enables on-demand creation for keys for SAs, i.e. Security associations, and facilitates the use of keys. This type of key management is actually used for large distributed systems with dynamic configuration. Furthermore, the default automated key management protocol for IPsec is referred to as ISAC-MP or Oakley. And then as a reminder, ISAC-MP stands for Internet Security Association and Key Management Protocol. These two consist of the following. First, the Oakley Key Determination Protocol. In short, Oakley is actually a key exchange protocol based on the Diffie-Hellman algorithm, but it does provide additional security. Additionally, Oakley is actually generic and does not dictate specific formats. Secondly, referring to ISAC-MP, it provides a framework for Internet key management and actually differs from Oakley in that it provides a specific protocol support, which includes formats as well as used for negotiation of security attributes. However, it is important to note that ISAC-MP by itself does not actually dictate a specific key exchange algorithm. Rather, ISAC-MP consists of a set of message types that enable the use of a variety of key exchange algorithms. It's also important to note that while Oakley is a specific key exchange algorithm, it is actually mandated for use with the initial version of ISAC-MP. So looking at that final bullet point, it's important to note that in IKEv2, the terms Oakley and ISAC-MP are actually not used. The terms are not used, and there are significant differences from the use of Oakley and ISAC-MP in IKE version 1. But like I said, while the terms aren't used, the basic functionality that I previously described is actually the same for IKEv2. And the rest of this presentation focuses on the specific IKEv2 specifications. Now moving on from the context of IPsec key management, we can continue digging into IKEv2, specifically the key determination protocol of IKEv2. As you can see on this first bullet point, IKEv2 key determination is actually a refined version of the Diffie-Hellman key exchange algorithm. As we recall from the previous class lectures and readings, specifically from chapter 10 in our textbook, Diffie-Hellman involves the interaction between users Alice and Bob, or A and B. Remember, there is actually a prior agreement on two global parameters, Q, which is a large prime number, and A, which is, lowercase a, which is a primitive root of lowercase q. A, or Alice, then selects a random integer, which is x sub a, as its private key and transmits to B, or Bob, its public key, which is y sub a. Similarly, B, or Bob, selects a random integer, which is x sub b, as its private key and transmits A to public key y sub b. As such, both A and B, also known as Alice and Bob, can now compute the secret session using the algorithm you see on this slide. Moving on, you'll recall that the Diffie-Hellman algorithm has two useful and important features. The first is that secret keys are created only when they're needed, and as such, there's no need to store the secret keys for a long period of time, which would normally expose them to increased vulnerability. Secondly, the exchange requires no pre-existing infrastructure other than the agreement on the global parameters. That said, don't forget that there are a number of weaknesses to the Diffie-Hellman, as discussed in previous class lectures. As a reminder, some of these weaknesses include not providing information about the identities of the parties, being subject to man-in-the-middle attacks, and being computationally intensive, and thus vulnerable to what are called clogging attacks. However, the good news is that the refinement of IKEv2 key determination is actually designed to retain the advantages of Diffie-Hellman while countering its weaknesses, and we'll explore that on the subsequent slide. As mentioned in the previous slide, IKEv2 key determination is designed to counter the weaknesses of Diffie-Hellman, and this is done by implementing these 5 features you see on this slide. Specifically, Feature 1 refers to employing a mechanism known as cookies to thwart clogging attacks. The second feature refers to enabling the two parties to negotiate a group. This, in essence, specifies the global parameters of the Diffie-Hellman key exchange. Regarding the third, it uses nonces to ensure replay attacks. And the fourth feature refers to enabling the exchange of Diffie-Hellman public key values, while the fifth one refers to authenticating the Diffie-Hellman exchange to thwart man-in-the-middle attacks. Concerning the first feature, the cookie exchange requires that each side send a pseudo-random number, which is known as the cookie, in the initial message, which the other side acknowledges. This acknowledgement is then repeated in the first message of the Diffie-Hellman key exchange. If the source address was forged, then the opponent will get no answer. Thus, an opponent can only force a user to generate acknowledgements and not perform the Diffie-Hellman calculation. Additionally, it is important to note that IKE actually mandates that cookie generation satisfy at least these three basic requirements. First, cookie must depend on the specific parties. Second, it must not be possible for anyone other than the issuing entity to generate cookies that will be accepted by that entity. And third, the cookie generation and verification methods must be fast to thwart attacks intended to sabotage processor resources. So in order to make things fast, the recommended method actually for creating the cookie is to use a fast hash, such as MD5, over the IP source and destination addresses, the UDP source and destination ports, and a locally generated secret value. Concerning the third feature, IKE key determination employs nonces to ensure against replay attacks. Each nonce is a locally generated pseudorandom number, as we discussed in previous chapters. Nonces appear in responses and are encrypted during certain portions of the exchanges to secure their use. Concerning the fifth feature, three different authentication methods can be used with IKE key determination. The three are digital signatures, public key encryption, and symmetric key encryption, topics all of which we've discussed in depth in earlier lessons and lectures. Continuing on from the previous slide of IKEv2's key determination features, you will note that the IKEv2 key determination supports the use of the 5 different groups you can see on this slide for the Diffie-Hellman key exchange. Of note, as this slide indicates, each group includes the definition of the 2 global parameters and the identity of the algorithm. Furthermore, the first 3 groups are the classic Diffie-Hellman algorithm using modular exponentiation. The last 2 groups use the elliptic curve analog to Diffie-Hellman, which, as you may recall, was described in the chapter 10 of our class textbook and accompanying lecture. In contrast to the previous 2 slides highlighting key IKEv2 features, IKEv2 is still not without potential weaknesses. And as you can see from this slide, there are 3 potential weaknesses that exist. Concerning the first bullet point, it is important to ensure different random choices are made each time for nonce generation, and to not assume that random choices are being made. Assuming and otherwise not ensuring different choices are made, then randomness may not be achieved. Similarly, concerning the second bullet point, key pair reuse is not recommended. Specifically, a group of security professionals showed that reusing a key pair across different versions and modes of IKE can lead to cross-protocol authentication bypasses, enabling the impersonation of a victim host or network by the attacker. And finally, regarding the third bullet point, in short, RSA and its use in IPsec and thus IKE is not perfect. And with the onset of quantum computing processing power, there will be enough processing power to run Shor's algorithm, and by doing so, ultimately breaking RSA, and in turn breaking IPsec and IKE. Now let's move on to the exchanges. The IKEv2 protocol involves the exchange of messages in pairs. This slide shows the first 2 pairs of exchanges, which are referred to as the initial exchanges. I have indicated each pair with a blue notation on the left side. Specifically, in the first exchange, which is the blue one, the 2 peers exchange information concerning cryptographic algorithms and other security parameters they are willing to use, along with the nonces and Diffie-Hellman values. The result of this exchange is to set up a special security association, which is also an SA, called the IKE-SA. This security association defines parameters for a secure channel between the peers over which subsequent message exchanges take place. Thus, all subsequent IKE message exchanges are protected by encryption and message authentication. In the second exchange, which I've indicated with the blue 2, the 2 parties authenticate one another and set up a first IPsec security association to be placed in the SADB and used for protecting ordinary communications between the peers. Ordinary means non-IKE. Thus, as you can see in total on this slide, 4 messages are needed to establish the first security association for general use. As you recall, the previous slide highlighted the initial exchange process. While continuing on, this slide highlights the subsequent exchanges, specifically the create child SA exchange and the informational exchange, as you can see with the blue text. Furthermore, as you can see, the create child SA exchange can be used to establish further security associations for protecting traffic. Additionally, the informational exchange is used to exchange management information, such as IKEv2 error messages and other notifications. During these next few slides, we will discuss header format, payload format, and payload types. You'll recall that IKEv2 defines procedures and packet formats to establish, negotiate, modify, and delete security associations. Well, this slide shows the header format for the IKE message. The IKE message consists of an IKE header followed by one or more payloads, which we discuss on subsequent slides. All of this is carried in a transport protocol. What's more, implementations must support the use of UDP for the transport protocol. Digging more into the header format, as you can see on this slide, it consists of the following 9 fields: indicator SPI, responder SPI, next payload, major version, minor version, exchange type, and flags. Regarding indicator SPI, that is 64 bits, and that refers to a value chosen by the initiator to identify a unique IKE security association. With regards to the responder SPI, that is also 64 bits, but that's a value chosen by the responder to identify a unique IKE SA. The next payload is 8 bits. This indicates the type of the first payload in the message, and there will be more on this in the next slide. The major version and the minor version are both 4 bits, but the major version indicates the major version of the IKE in use, and the minor version indicates the minor version in use. With regards to the exchange type, that's 8 bits, and it indicates the type of exchange, and that is also discussed more in depth a little bit later. Regarding flags, those are 8 bits, and they indicate specific options set for this IKE exchange. Regarding the final 2 items, the message ID and the length, those are both 32 bits. The message ID is used to control retransmission of lost packets and matching of requests and responses, whereas the length, that indicates the length of the total message, which is actually the header plus all payloads, and this is identified in using octets. As promised on the previous slide, we will now look more in depth at payloads. As a reminder, as part of the security association establishment, IKE defines payloads for exchanging key generation and authentication data. So these payload formats actually provide a consistent framework independent of the specific key exchange protocol, encryption algorithms, and authentication mechanisms. Additionally, all IKE payloads actually begin with the same generic payload header, as you can see on the slide. The next payload field has a value of 0 if this is the last payload in the message, as you can see on these bullet points here. Otherwise, if its value is the type of the next payload. The payload length field then indicates the length in octets of this payload, which includes the generic payload header. Furthermore, the critical bit is 0 if the sender wants the recipient to skip this payload, if it does not understand the payload type code. Conversely, if it is set to 1, that means the sender wants the recipient to reject the entire message if it does not understand the payload type. In the previous slide, I briefly mentioned payload types and where the notation is made in the payload format. This specific slide summarizes the entire list of payload types defined for IKEv2 and lists the fields or parameters that are part of each payload. Going down this list, we will discuss each one within my blue bracket notation a bit more in depth. First, let's discuss the security association type, which is the first one on the list. In short, the security association payload is used to begin the establishment of an SA. The payload has a hierarchical structure and may contain multiple proposals. What's more, each proposal may contain multiple protocols, while each protocol may contain multiple transforms. Additionally, each transform may contain multiple attributes. In sum, these elements are formatted as substructures within the payload as proposal, transform, attribute. Here's a bit more on each. Regarding proposal, this substructure includes a proposal number, a protocol ID, which is AH, ESP, or IKE, an indicator of the number of transforms, and then a transform substructure. Regarding transform, different proposals support different transform types. The transforms are used primarily to define cryptographic algorithms to be used with a particular protocol. Each transform may include attributes that modify or complete the specification of the transform. An example would be key length. Now moving on to the second type, where we see here on the slide is key exchange. The key exchange payload can actually be used for a variety of key exchange techniques, including of course Oakley, Diffie-Hellman, and RSA-based key exchange, which is used by PGP, which is pretty good privacy. The key exchange data field contains the data required to generate a session key and is dependent on the key exchange algorithm used. Moving on to the third type, which is identification. The identification payload is used to determine the identity of communicating peers and may actually be used for determining authenticity of information. Typically, the ID field will contain an IPv4, IPv6 address. Now, with regards to the certificate payload, which is the fourth on our list, the certificate payload actually transfers a public key certificate. The certificate encoding field includes a type of certificate or certificate-related information, which actually could include some of these. PKCS wrapped in the X509 certificate. It could be PGP certificate, a DNS signed key, an X509 certificate, signature or key exchange, Kerberos token, certificate revocation list, which is a CRL, or an authority revocation list, which is an ARL, or even SPKI certificate. In any case, at any point in an IKE exchange, the sender could actually include a certificate request payload to request the certificate of the other communicating entity, which is actually the fourth item on this slide here. Regarding the sixth item, the authentication payload, the authentication payload actually contains data used for message authentication purposes. The authentication method types so far that are actually defined in this could be the RSA digital signature, the shared key message integrity code, as well as the DSS digital signature. And then of course regarding a nonce, we've looked at nonces a lot throughout this class. The nonce payload actually contains random data used to guarantee liveliness during an exchange and to protect against replay attacks. Now looking at the last item in this blue bracket on the slide, the notify type. The notify payload actually contains either error or status information associated with the security association or the negotiations. We'll actually come back to this slide, but for now, let's take a further look at the types of notifications, digging into notify a little bit deeper. One of the most significant lessons learned throughout this project is that an advanced understanding of Splunk and SPL is required to effectively identify and perform threat hunting with Splunk. Without the advanced knowledge of the tool itself, as well as a deep understanding of how Splunk is integrated and configured within an organization, effectively mapping SPL commands to indicators of compromise will prove to be difficult. As such, it is imperative to study and become familiar with the common SPL commands and uses, as well as how Splunk Enterprise or Splunk Cloud is installed. and configured in an organization's computing environment. Another lesson learned involves ensuring data remains protected. In other words, Splunk has access to many types of logs and data, and quite often certain data types such as sensitive, i.e. credit card numbers, secrets, credentials, etc., or classified data, may end up in a log when it was not meant to be there. As such, it is imperative that as an SPL commands are used, and logs and data subsequently displayed, the threat hunters be aware and sensitive to detecting data and logs when they shouldn't be there, and quickly act to mitigate the issue by bringing in appropriate teams. As promised, let's elaborate a little bit on the notify payload type mentioned on the previous slide. As you can see from this slide, the following table lists all of the IKEv2 notify messages. It is important to note that these messages are broken up into two categories, error messages and status messages. Regarding the error messages, you have unsupported critical, payload, invalid SPI, invalid major version, invalid syntax, invalid payload type, message ID, as well as invalid SPI. For the status messages, we have initial contact, set window size, additional TS possible, IP comp supported, NAT detection source IP, NAT detection destination IP, cookie, and use transport mode. Now, moving on and discussing the second part of the payload types slide, let's continue discussing the remaining payload types, as I've indicated on my blue bracket on the left. The first one here is the delete type. Now, the delete payload actually indicates one or more security associations that the sender has deleted from its database and is of course then no longer valid. Concerning the vendor type, the vendor ID payload actually contains a vendor-defined constant. So in short, these constants can actually be used by vendors to identify and recognize remote instances of their implementations. Concerning the traffic selector type, this payload type allows peers to identify packet flows for processing by IPsec services. With regards to the encrypted payload type, this payload type contains other payloads in encrypted form. Now, the encrypted payload format is actually similar to that of the encapsulated security payload, or the ESP, which is actually something that was discussed in an earlier chapter of our class textbook. Similarly, the encrypted payload type may actually include an initialization vector if the encryption algorithm requires it, and as well as an ICV if authentication is selected. Moving on to the configuration payload type, this payload type is used to exchange configuration information between IKEv2 peers. And finally, regarding the Extensible Authentication Protocol, which is also known as EAP, this payload type actually allows IKE security associations to be authenticated using EAP. And this was actually something that was discussed in Chapter 16 of our class textbook. Wrapping up today's presentation, we take a look at what Internet Key Exchange is. We looked at a lot of the context as well as IKEv2 determination protocols, key determination, supporting groups for key exchange, potential weaknesses of IKEv2, as well as initial exchanges and subsequent exchanges, as well as the header and payload formats, the specific payload types, and notify messages. As noted on this slide, these are the major references I consulted to develop this presentation. Thank you all for joining. This concludes my presentation.